This video is going to be brief, I hope, and it's going to deal with essentially with particle physics. Um, so the idea for this is we need to explain what's going on inside of stars, and to do that, we need to explain what is inside stars at very, what is the basic units. And you've seen, if you've taken chemistry or paid attention in your other science classes, you know what, you know how atoms are made. We're going to go just a little bit beyond that. So we'll go through a few things. You know, this is mostly trying just to hit the highlights. We're not trying to, you know, have a complete understanding of things because that takes years and years and years, and it's a field that's still being studied. So, anyway, we've talked about some of these things already. All right, is talk about light, which behaves like waves, but it also behaves like particles. But those particles are not like, it's not like throwing a brick or a baseball. It's not a tangible thing. It's a very different thing than what you're used to. Um, we talk about atoms. Atoms are mostly nothing. The particles that make up atoms are very, very distinctly small compared to the atom. We talked about the energy levels in atoms. Electrons are restricted to particular energies. So understanding all that stuff is quantum mechanics, understanding all the details of that. Um, and the thing of it is, we always describe the elemental particles, the electrons, protons, and neutrons, we describe them as fundamental. Um, right? And before that, we described the atoms as fundamental. Right? The idea of something being atomic means you can't divide it. But then we found new particles that build it up. And now for protons and neutrons, we find particles that build those up, what are called quarks. Um, we find other sorts of particles which are like mirror images. The antimatter, which is basically the mirror image of matter. It's almost exactly the same, but it differs in charge. And so having something in its mirror image is going to allow interesting stuff. We talked about forces, and when we did, we talked about gravity and we talked about Newton's laws. Ultimately, all the things you can think of, if you imagine throwing a brick, or you imagine petting a cat, you imagine friction or magnetism, all of these things end up falling under four fundamental forces, which we'll talk about. All right, and then we talked about light, which we think of as a wave, but we also think of it as a particle. Well, it turns out that these fundamental particles can also be looked at as waves. They You can describe them with a wavelength and a frequency, and the key and important thing here is that our understandings of fundamental particles that we develop in labs and in particle colliders, that understanding applies to how things work astronomically. So we also rely on an awful lot of quantum mechanical understanding for everything we do. Uh, Everything, your radios, your television, cell phones, computers, all of that stuff has transistors in it, which use quantum mechanical effects to act as switches or amplifiers to control electrical signals. So everything that we do in the modern world bears some necessity of quantum mechanics. Without our understanding of quantum mechanics, it wouldn't be possible. And much of our understanding comes from smashing together particles and trying to find new ones in particle accelerators. When we talk about particles, it's kind of important to talk about sort of the fundamental properties. How do we categorize particles? So there's really three basic quantities. Every particle has a certain mass. You can tell them apart by mass. Every particle has a charge associated with it. That charge might be zero, or it might be positive or negative, and it might be more than one, but it comes in certain amounts. And never like 1.5 of the proton's charge. It's always 1 or -1 or 2 or -2. It's always integer multiples of the electron. And then particles have spin. They're not inherently spinning like a top, if you imagine something spinning, but they have an amount of angular momentum as if they were. And it's just something you have to account for, that they have. And so particles have different amounts of spin as angular momentum. And that's basically about it. Everything else is categorization. But you can divide up particles by these properties. Right? So to explain spin a little bit, we assign a direction to it. It's either up or down, so positive or negative. But it's always going to be for the stuff we're talking about as real matter, real particles that we deal with every day. The particles have integer or half integer multiples of a particular constant, h divided by 2 pi. H here is Planck's constant, which we talked about sometime in the past. H is Planck's constant is a very tiny number, 6 times 10 to the minus 34 joule seconds. Those are 2 units multiplied together. But that is, it's a measure of the angular momentum. And so these particles have a little chunk of angular momentum, and that points in some direction, up or down. It tells you essentially it is, if it's spin up, it rotates like the Earth does. If it's spin down, then it rotates like an upside down globe. It spins the other way. So, that's our ideas of orientations of spin. So, the very fundamental things. Right? So this image is showing like a proton and a neutron, and there are constituent particles that make those up. It's a little easier to talk how would he classify them, and we classify them based on spin. The idea is that if things have integer spin, there's things that look like light, and we call it bosons. If things have half integer spin, they're like atomic particles. They're like electrons, protons, neutrons. We call them fermions. That gives us a nice 2 categories to divide things in. And the basic understanding you need is that fermions are matter. Right? Fermions are the things that make up matter. And bosons are the things that transmit forces. They're interactions between fermions. So everything that's like a photon is light goes from some object to some other object. So those fermions can be divided up into 2 other groups. One is things like electrons. Electrons are small, and they have some associated particles with them, neutrinos, which we'll talk about. Those are what we call leptons, just your basic kind of small stuff. And then the other categorization is groups of quarks, which is the things that make up protons and neutrons and the other sorts of particles one might see. So quarks are kind of just building blocks. There's 6 types. For protons and neutrons, we only need 2. We call them up and down. And they have fractional charge. The up ones are plus 2/3. The down ones are minus 1/3. So in a proton on the left, you have 4/3 up, so plus 4/3 minus 1/3 down. That gives you plus 1. And so proton has positive 1 charge. So for the neutron on the right, you have minus 2/3 down and plus 2/3 up. So you have 0 charge. So it's neutral. So these quarks are just building blocks. And this is the thing, we've never seen them alone. We've always seen them in groups, in constituent, piled together to make something. But we can do experiments to deduce their properties and, to deduce that they exist within the particles. So there's 6 types. The other types make other sorts of particles that are quite unusual. Leptons also come in 6 types. So I talked about the muon when we talked about relativity. It's the fat electron. And then the tauon is the grossly fat electron. It's even larger. But fundamentally, they're kind of the same type of particle. They're just different masses. And then each one has a neutrino. Neutrinos are these very light particles that basically don't interact with anything. They're light, they're uncharged, but they exist because there's certain other properties that when you see an interaction between particles, certain things are conserved, and the neutrinos show up when you need to conserve particular quantities. All right, I had to pause for a moment. All right, so every type of particle has an antiparticle, has a particle that is exactly the same except for its charge. And these pairs of types of particles, for example, the electron is matter, and its mirror image, the positron, has a positive charge, or it's also called the anti-electron, is antimatter. Pairs like this can, when they meet together, they can annihilate. They can turn themselves into energy, photons. And so the properties of these particles, right, they have mass. Well, that gets turned into energy. That's from relativity. They have charge. Well, you have 0 charge before they meet, and you have 0 charge after. The photons have 0 charge. They have angular momentum. And, well, there might be 0. There might be 1 up and 1 down. And that goes away. Or they might be both up or both down, which means the photons have angular momentum. Right, so that gives you some more information. But the gist of it is all the properties that exist in the electron and the positron together have to exist in whatever comes afterwards, in the photon. So when particles collide with antimatter, they can annihilate. Now, you're not going to see a mix of these things. You're not going to see like a proton and a positron. Right? You have to match things of the same type as matter and antimatter. But generally, that's not hard, because if you make antimatter, it is surrounded by matter. It will find something and annihilate. So you can do any of these atomic processes. You should be able to do them backwards. So you find 2 photons with the right amount of angular momentum, and the right amount of energy. You need sufficient energy. You focus those photons in the right spot, and you'll form two particles. This is what's called pair production. This is, in a sense, a way of generating antimatter, is to focus enough energy in one spot that particles show up. So we talked about matter. Everything we talked about so far, the quarks, the leptons, all the antimatter particles, those are all matter. Those are all sort of the fermions. So the forces have particles associated with them. And so going back to the quarks, if you look at proton, it has a lot of positive charge in two different particles. It should repel each other electromagnetically. The force that holds those particles together and makes the thing a proton is what's called the strong nuclear force. That's what holds nuclear particles together. And so there's a particle associated with that force. It's called a gluon, and it's named that because it glues the particles together. It gets stronger as you stretch particles apart, like a spring. And so each of these particles are passing gluons between each other, and it acts to attract the particles together. So we have electricity and magnetism are covered by one electromagnetic force. That is the thing that holds electrons and atoms and does other interesting stuff. And light, photons, is what carries the force between particles. All right, so some nuclear reactions are governed by what's called the weak nuclear force, which is really, it touches electromagnetic forces. But it's very, very kind of distinct. Think of nuclear decay. Right? It's the thing that causes a nucleus to break apart in fission or to send off radiation and decay slowly. So these weak forces are mediated by weak bosons. And then there's gravity, which we haven't talked about particles for gravity at all. We've talked about gravitational waves, and once there was a sort of a correlation where light is both a wave and particle, you can think, well, maybe gravity's like that. We can find gravitational waves, so maybe there's gravitational particles, what are called gravitons. Finding a thing localized enough to call it that is impossible, as far as we know. Gravitational waves effectively take up massive amounts of space-time. They're not localized at all. So there's a theoretical idea of this particle that carries energy the way gravitational waves do. But gravity holds together large accumulations of matter. So we talk about the strength of these forces. We compare everything to the electromagnetic force. And the strong force is strong. It's 100 times stronger. The weak force is weak. It's 100,000 times weaker. Gravity is massively, massively, massively weaker. And this is inside the nucleus, though gravity is really weak outside. It's independent of a nucleus. Um, the way to think of gravity is, if you have a piece of paper, it takes the earth to hold it down on the table or on the floor. But if you take a cat and you pet it until you have some static electricity on you, you can pick up that piece of paper with static. All right, and it doesn't take that much. You rub a cat's fur or run your hand through your hair, or pieces of tape. All right, this is a thing you should do at some point. Get two pieces of clear tape. lay them on a table, rip them off the table fast, and then wave them around and see how they interact electrostatically. We'll show that video sometime in the future. Anyway, outside the nucleus, the biggest thing that matters is gravity and electromagnetism. But inside the nucleus, you have forces holding the particles together in the nucleus and holding the constituent particles in the atomic particles. So there's a whole lot of stuff we have trouble explaining. Like when we talked about electrons, we talked about they have a specific energy that they're confined to in an atom, which is interesting. We didn't say a particular location. In your head, you might have an image, right? If you do not remember your chemistry well, you might have an image of electrons orbiting the nucleus like planets orbiting the sun. And in a sense, that's a model that sometimes works, but sometimes you need a better understanding. And the truth of it is, electrons are just kind of all over the place. There's a probability of detecting an electron in a particular location. And really, it's just cleaner to talk about with a particular energy or being in a particular energy level. Is that electrons are just a cloud around the nucleus of an atom. And the gist of it is there's a relationship between the momentum of a particle and the location of it. And you essentially cannot know them, the pair of those, momentum and location, arbitrarily accurately. This is what's called the uncertainty principle, is that there's an uncertainty in your ability to measure the position and location. And it's not anything to do with the measurement. It's a fundamental limit, is that if you try to make a measurement, you're going to change. If you make a measurement of the position of an electron, you change its momentum completely, and you only know it in one instant. If you measure its speed, you have to measure it over some distance, and you don't necessarily know where it is in that distance. But it's no matter how you try to trick yourself out of that, there's no way around it. These things are not relatable. You can't know both of them at the same time perfectly. And that's unintuitive to us. If we take a tennis ball and we bounce it, we could know exactly where it is at any given instant. But particles don't do that. They have one well-defined thing at a time. So for electrons, you may have seen these images in chemistry class. You really just know the probability of finding the electron somewhere, or of it having a particular energy. And a lot of times it's interesting to treat electrons like waves. If you define a momentum, well, light has momentum. All sorts of waves carry momentum and energy, but they don't necessarily have a nice position. You can treat electrons like waves. They have a wavelength. So, in math terms, the uncertainty in the location times the uncertainty in the momentum equals approximately this Planck's constant, which is not originally how it came up. It came up when we were talking about black body radiation and trying to find that curve that we kept talking about the intensity and temperature relationship. But it keeps coming up over and over and over again, and it's more fundamental than that. But essentially, location and momentum, the product of their uncertainties, is about Planck's constant, which means you have a limit. You can't know it any better than that. And interestingly enough, you can convert location to time and momentum to energy, and you get the same relationship. And there's a fair number of variables like this where you can take pairs of them and you can only know a pair of them within this uncertain relationship. So there's another principle, what's called the exclusion principle. And if you had to learn in chemistry class about electron shells, this is why you had to do that. So if you remember, so for those of you that didn't take chemistry, the deal here is when you have electrons in an atom, they go in certain energy levels, and only so many electrons can go in a certain energy level. Then you have to put extra ones in outer energy levels with slightly higher energies. So those of you in chemistry know some of the details about this. You know that the innermost level has 2 electrons, and the next one will have 6. 2 and 6, and then the next one will have 2, 6, and 10. I think, yeah. And so you might not necessarily know where those are coming from. And what's going on is we're talking about particles, electrons, that have exactly the same mass and charge. The only other thing we can do to distinguish them is talk about their angular momentum. So for the exclusion principle, we define quantum state, which is describing the momentum, the orbital angular momentum, which is its angular momentum because it is associated with a nucleus, its spin, and its charge. We can do things like, try to interact a positron instead of an electron, but we'll just deal with electrons for the moment. Though this is true of all particles when I state the exclusion principle. But we're going to talk about in atoms, usually electrons. So momentum is essentially mass and velocity. So you can do things like change electrons with muons, and it just changes its momentum and angular momentum a bit. So we defined a quantum state. It's the things you can know about a particle. The exclusion principle says that if you have 2 fermions, they cannot share the same quantum state at the same time. Now, that does not apply to bosons. Light can have millions of particles in the same state. But any sort of matter made up of fermions obeys the exclusion principle. So in terms of electrons, you start with hydrogen. It has 1 electron. It can be either spin up or spin down in the lowest state. You go to helium, it has 2 electrons. You have one that's, say, spin up. The other one must be spin down. Otherwise, they would both have the same energy, the same mass, same charge. They would have the same location, essentially, the same orbital and spin angular momentum. And so they would share the same state. So they must be one spin up, one spin down. You go to the next element, lithium. It's got a 3rd electron, but it cannot fit in this lowest state because it only holds 2. This lowest state, the lowest energy, it represents essentially 0 orbital angular momentum. So it has to go to the next one out, which is 1 angular momentum in units of like h bar over 2 pi. So it goes to the next one out. Well, this has slightly higher energy, which means it has a slightly higher momentum. And so this has 3 orbital angular momentum states, 1, 0, and -1, and 2 spin states, which means it has 6 possible states. So all the next electrons from lithium to neon can fit. There'll be another energy level that has two, and then one that'll have six, and so you can put in eight more electrons. And you build up all of the shells that you learn about in chemistry through this exclusion principle and from stating what the angular momentum of each shell and subshell is. Again, you're listening to a physicist describe chemistry. Ask Mr. Brown if you want more details about it, or if you want the proper, technically correct answers to this. So that's the exclusion principle. Now, the exclusion principle leads to some interesting details. And so we want to talk about stars. We're just going to get into the details of they're a big ball of gas. Why don't they just collapse on each other? Why doesn't all the stuff fall to the center of the star at once? Well, in a star, there's particles and they're moving around and they're going to collide with each other. Or if they're charged, they may repel or attract each other. But the gist of it is you can treat them as pushing on each pressure. If the particles are moving, they bounce off each other and that creates an outward pressure. If they're moving faster, there's a higher pressure. In this case, in the picture, it's shown as a balloon. If you cool the balloon down, it shrinks. And as you heat it up, it expands because the molecules inside are bouncing faster and faster. They press outwards harder, and that pushes the balloon outwards. So the same sort of thing happens to normal stars. There's a source of heat, keeps the particles moving fast, and it keeps an outwards pressure which counteracts gravity. So say that source of heat disappears. You run out of fuel in a star, and it cools off. Well, the particles themselves cannot collapse completely down to a single point by themselves. Eventually, they start running into each other, and as they compress further and further together, you're restricting the location of the particles, which means that the momentum increases. It gets faster and faster and faster. And I need to take a pause for a moment. Hello, students. My cat made a shambles in my room, so I had to stop for a second. I'll show you some pictures of them. Look at the physics videos; they'll show up. So, where were we? If you have a star, you have the particles trying to compress together due to gravity. They pull each other together. They're gravitationally attracted. Normally, you have thermal pressure keeping the star supported, keeping it a fixed size. It doesn't just continually contract. But sometimes what you have is, as the star contracts, you're locating the particles in a more confined space, which means their momentum goes up. And particles eventually get into a state where they're nearly forced to share a quantum state, and they can't do that. And so what happens is particles increase their momentum, that presses outwards. And as you confine the particles' location, you increase their velocity, and they bounce around and hold up the star effectively because you can't force them into the same state. This is where frequency pressure. And this will come up when we talk about stars that are dying, that are running out of fuel. Right. There's a couple different types. Generally, the thing that happens in stars is electron degeneracy pressure. The electrons can't be localized. If that fails, what generally happens is the electrons, instead of confined into the same quantum state, they pair up with protons and they form neutrons, and you're left with neutron degeneracy pressure, which is a bit stronger because they're more energetic particles. They have larger mass. And so that becomes even more difficult to squeeze down. And then after that, well, we kind of don't know for various reasons. Um, we don't know if there's something beyond this, where like pairs of neutrons pair up or something, or if we just can't figure out what it would be. All right, so because of this uncertainty, right, the uncertainty principle, exclusion principle are going to be the big things that matter. And the exclusion principle tells us how some stars exist at a particular size and shape without thermal pressure. So the uncertainty principle will tell us how stars exist at all, in a sense. And the idea is that since the position or the momentum of the particle is uncertain, it's fairly easy to measure the particle in a position that it shouldn't necessarily be in. You can imagine, the example here in the notes is a person in jail. Jail has bars and you can't get through the bars. You don't have the means to do it. Can't crash through by energy, just bounce off of them. An electron clearly could, but imagine a situation where you could confine an electron in a sense. Just because you can confine it to where it shouldn't have enough energy to get out doesn't mean it can't actually get out. It just lowers the odds of it getting out. There's still probability of measuring it having tunneled through a barrier and getting out of a confinement. So where in the sun, protons are all positively charged. They can't get close enough together for fusion to occur. We'll talk about this when we talk about uh, the sun and stars. The protons should be repelled. So there's a barrier that prevents them from getting close enough together to fuse. However, quantum tunneling allows the protons to occasionally get close enough, even though they should be repelled, and that's sufficient to allow what fusion we do see. Because you can generate matter and antimatter in equal amounts out of energy, space isn't really empty. Effectively, there's an uncertainty in energy, so you can just borrow a little bit and make some particles. Now, generally what happens is these particles pop into and out of existence all the time because the uncertainty in energy is associated with an uncertainty in time, and those are both very small. All right, for enough energy to make a pair of particles, you have a very small amount of time uncertainty. So you can create the particles, and then very shortly that energy has to be energy. It can't be matter. So the particles have to annihilate. Unless you have an outside source of energy somewhere, right? So normally that source of energy is light. You have light, creates the particles. Particles might travel far enough apart, or they might annihilate and you have light again. So these particles, since we usually never see them, are constantly being formed and created, pair produced and then annihilated. But if you can make one of them exist long enough, then it becomes a real particle. That's the trick. So effectively, all of empty space is really full of particles that show up and then go away, and they're just borrowing energy that sits in the background, what's called vacuum energy, which is just the uncertainty in the actual energy in space based on whatever else is there, light and the curvature of space and the uh, particles that are already there. There's just a background energy they can borrow from. So this leads us to a question. What happens around weird things like black holes? We very briefly talked about black holes as things that matter can't get away from. Is that there's a place where you cannot see within, you can't see events inside of it. And light can't get away. So let's say that around that black hole you have these virtual particles forming. Well, what happens if one of them falls in and the other doesn't? Then they can't annihilate. You have a particle that's formed. So you have effectively, it looks like the black hole is producing these particles that are somehow escaping. So you can ask, well, where does that come from? Well, you have three things. You have the two particles you just created, and then you have the black hole, which has some quantum state. It has some charge. That charge might be zero, but it has some. It has some angular momentum. It has some mass. So when one of these particles falls into the black hole, somewhere in the black hole, it has to go away. It has to give up that energy. And it ends up taking the energy out of the black hole. What it ends up doing is the particle that survives steals energy from the black hole. And so slowly, it looks like black holes radiate particles very slowly. And that was an interesting thing, is black holes are perfectly absorptive, you would think, which means from the point of view of the light radiating from an object, like we talked about in chapter 5, it's a black body. It has to have a temperature and it has to radiate something. And so you can define a temperature, and that was Hawking's sort of big thing. So Hawking, if you're not aware, his big thing was having big ideas and then having grad students do a lot of the research on it. And so he said a grad student the problem of defining the temperature of a black hole. Turns out it's the surface area. It's the surface area of the event horizon. So Hawking predicted that black holes radiate. This is a way for them to radiate, what's called Hawking radiation. These particles escape. One particle escapes in a virtual pair, and the other particle is absorbed, and it causes loss of mass. The black hole evaporates over a long time. That's kind of a really weird thing. We don't have any evidence of it, except for black holes of a certain mass that formed early in the universe should be evaporating now. So it's possible we could see something if those black holes exist. We don't know. So, interesting idea, possible. There's nothing that would prevent, a virtual pair forming and then one being absorbed by the black hole. We just, we need to observe it. And that concludes quantum mechanics. So let me go back for a moment. I want to hit the very, very important bits. So I'm not going to do everything here. You're seeing a lot of properties of particles are important. Know that. And understand what we mean by spin in particles. You need to know fermions and bosons. You need to know quarks and leptons. You need to know about matter and antimatter. The four forces are nice to know. The uncertainty principle is definitely important, and the exclusion principle is definitely important. You need to know the two principles, and then the consequences of those. Degeneracy pressure is going to come up chapter after chapter after chapter. You need to know at least what it is. And Quantum tunneling will come up when we talk about stars, so you need to know about it. Don't worry too much. A lot of stuff will come up when we talk about the particular thing. Virtual particles will come up when we talk about black holes. All right, that concludes the video. I'm sorry for all the pauses. I've got sniffles in the nose, and I've got cats that are running amok. So, you know how that is. Keep working on your homework. Let me know if you have any questions, and we'll see how things go.